because it has more electrons than protons. If I have less electrons, then I would have more protons than electrons, and so my particle would have a net positive charge. A particle that has a net positive charge is called a cation. A cation carries a positive charge, and anion is the opposite. An anion is a particle that carries a negative charge. So when we're talking about atoms, the cation has less electrons than the element. An anion has more electrons than the element. And if we're talking about a molecule, then a cation has less than a full octet, and an anion has more than that. So that is just a basic definition of what the anion and cations are. So why are they called cation and anion? When Faraday in the 1830s, 1840s was doing his experiments with electricity, and he was for the first time figuring out how this thing works, and he kind of came up with, accidentally I should say, with inventing a capacitor and a battery and all that stuff. He had these jars of electrolytes that he connected to his electricity generating machine, and he showed that those jars of electrolytes can store electrical power. And the way he realized that they store electrical power is that he told his lab assistant to go grab one of those jars. He went and touched the jar, and he got immediately electrocuted and died. And Faraday's first thought was, oh my God, I can store electricity. And batteries were born. So Faraday was doing these experiments, and the way his lab was set up was that his electrodes were in an east-west direction. And so he saw that that current in his system, in his convention, goes from cathode. Goes from cathode to an anode. So cathode is a negative, and anode is a positive electrode. So anions are ions that are attracted to the anode, because anode is positive, anions become negative, and cations are ions that are attracted to cathode. So why is that east-west thing important? Because cathode means means on your way down. Anode means on your way up. So anode was on the eastern end of the electrodes, and cathode was at the western end. And so he analogized to the sun going up and sun going down. So on the east side, the electricity went up. It was the electricity would go down. So that was a cathode. On the west side, electricity would go up. The other way around. East side goes up, anode. West side goes down, cathode. So it's a completely arbitrary nomenclature. Has absolutely nothing to do with reality, except that we're stuck with it. And those who study electricity first and then talk about the ions which is basically all of us, we get really confused about cation and anion versus cathode and anode at first. But keep that in mind. So when we're talking about organic compounds, that's on slide 3, the charge can be carried either by a carbon atom in the compound or by another atom in the compound. If it's carried by another atom other than a carbon, we just call it an ion, or we give it the name of the ion. So for example, what I've shown in the top line is the negative charge is being carried by an oxygen, so that's an anion. It's a or we can call it a carboxylate anion because it's an anionic form of the carboxylic acid. So with these, we either call them carboxylates, using their chemical names, or just pure say anion. But what happens when the charge is being carried by the carbon? If the carbon is carrying a positive charge, then hold on a second. Anyway, the positive negative charges kind of got moved around when I converted to this. Let me. Anyway, it doesn't really matter. So we see on the left side, the positive charge is being carried by the central carbon. Because the carbon is positively charged, it's a carbocation. And on the cations were positively charged particles. This is a carbon, so carbocations. And when the carbon carries the negative charge, we will call that a carbanion. Anions carry a negative charge, and so negative on the carbon, we get to be a carbanion. George Olah, who died in 2017, was a professor of chemistry at the University of Southern California, and before that, somewhere else. I don't remember where. And so in 1990, he basically, his entire career was understanding carbocations. Before George Olah, there was people knew about carbocations, but didn't know exactly what was going on. Olah, he dedicated his entire professional life to the study of carbocations. And in 1994, he won the Nobel Prize for that, a very, very well-deserved Nobel Prize. But news people would call them carbocations. So this is not a carbocation, it's a carbocation. So on slide 4, we'll see this is bugging me. Sorry, this formatting all got mixed up, and I don't know why. So I'm trying to kind of fix that so things actually make sense. All right. Something like that. Very good. Okay. So on the top line, we have the carbon attached to an X. That X could be anything. And the carbon, we have carbons have 4 bonds around them. So besides X, there are 3 other groups. We're not concerned about that because we are only looking at the carbon X bond. We said a million years ago at the very beginning of the series that chemistry, in effect, is the study of where the electrons go. So keeping track of the electrons is really the job of a chemist. And so in the top reaction, we look at the electrons in the bond between C and X. And let's say X grabs all of those electrons in the bond, all of them meaning both of them, and goes away. Now, X, in this case, will end up with one additional electron than it had before. Because in the covalent bond between C and X, X brings in one electron, C brings in one electron, and then in the covalent bond, they share. When X leaves, it not only leaves with its own electron, but it takes the other electron that was in the bond, meaning the one that belonged to carbon, it takes that along with it. So now it has one additional electron than it did before, so X ends up with a negative charge. We look at carbon. Carbon here has 3 bonds around it in the carbocation. Each bond, again, has 2 electrons for a total of 6. But we see that, again, in each bond, carbon brings in 1 electron, and the R group brings in another electron, and they share those 2. And so if I count the electrons around carbon, I only count 3, right? Half of the number of bonds, because the other half of electrons are coming from the R groups. So carbon here has 3 electrons. Neutral carbon has 4 electrons in its outer shell, and so carbon has 1 less electron than the neutral atom, and so the carbon will carry a positive charge. I can dissociate the carbon X bond another way, such that carbon now grabs all the 2 electrons in the CX bond. And here the analysis is exactly the opposite. Carbon now has 5 electrons around it, right? 3 that are involved in bonding with the R groups, and 2 that were the electrons of the CX bond. So we have 5 electrons around carbon. That's 1 more than the neutral atom, so carbon will carry a negative charge. And X has lost an electron, the electron that was involved in bonding with carbon. It has lost it to carbon, so now X carries a positive charge. So this is kind of an electronic look at how we can form carbanions and carbocations, starting from organic molecules, by checking to see how the electrons move. Are there any questions so far? Okay. This is going to go really fast. So we kind of so the question is, which one of these is going to happen? Is it that X going to grab all the electrons and leave? Or is it that carbon is going to grab all the electrons and kick X out? And the answer is that both of those can happen, and it all depends on the thermodynamic stability of the ion that's formed. If I can stabilize the carbocation as opposed to the carbanion, then I will create a conditions for carbocation formation, and vice versa. I can make conditions such that the anion of carbon will be more stable, and so a carbanion is formed. To understand what factors affect the stability of carbon, and today I'm only in the next 2 or 3 slides, I'm going to focus on carbocations. In other lectures, we're going to go back and talk about carbanions. Because so far for what I'm discussing, what we're going through, carbocations are a lot more important and are a lot easier to understand. So we're going to do that. So before we talk about how these things are stable, we have to learn a little bit of a naming conventions, and that starts on slide 5. This is a naming convention that we use to know how many other carbons are connected to the carbon of interest. Carbon of interest is the carbon at which the reaction is taking place, the reactive site of the molecule, the reactive site of the molecule. So if the carbon atom is standalone, meaning that it's a methane derivative, or if it's connected to another carbon, and the chain on the left-hand side could be as long as you want it to be, the carbon of interest is only connected to one other carbon. That's a primary carbon. If it's connected to two other carbons, there's one on each side. Again, those black carbons could be part of a chain that goes on forever, but the carbon in the middle is only attached to two. That's a secondary carbon. And likewise, at the end, we have a tertiary carbon, a carbon that's connected to three other carbons. We also have a quaternary carbon, a carbon that's connected to four other carbons. And almost all quaternary carbons are inert. Under normal reaction conditions, right? We could like heat it up and put it under tons of pressure, or do it in a vacuum, things like that. But under normal, benchtop solvent-based chemistry that we do, quaternary carbons are inert. So we don't talk about those in reaction chemistry. We talk about those in structural chemistry. So I'm not going to talk about them now. So how do all of these come together in a molecule? So if we go to slide 6, I have 2-methylbutane or isobutane, and I see from right to left the CH3 that is only attached to one other carbon, which is the CH2. And so the CH3 at the rightmost end of the molecule ends up being a primary carbon. The one next to it, CH2, is connected on the right side to the CH3, on the left side to CCH32H. And so that's a secondary one. And the carbon that has 4 bonds attached to it as drawn, you can see it, that has 2 CH3s and 1 CH2 attached to it. So those are 3 carbon atoms. So that's a tertiary carbon. Now, as you can see, these, at least structurally, are different from each other, right? One only has 3 hydrogens around it. The other one has 3 carbons around it. Those are structurally different. And if they're structurally different, chances are that they are also electronically different. So we go to slide 7, and we ask ourselves, what are the factors that affect the stability of a carbocation? First is physical, second is electronic. So in the physical, we call it steric hindrance. or the sterics of the molecule. Steric mean, I don't know what the dictionary definition of steric is. Let me, uh, oh, it says steric me. Oh, steric apparently only has a chemistry meaning, and it's the spatial arrangement of atoms in a molecule. That's sterics. And so steric hindrance means that the arrangement of the molecules, the arrangement of the atoms in the molecule is hindering the reaction, or is hindering what is hindering another species to come in and react with the carbon. And so the more crowded it is, you have the less opportunity for reactants to react with the carbocation. Meaning what? Meaning that if I form the carbocation in a very crowded environment, then other species, that are in the solution, can't get to that carbon that has the positive charge, and if they can't get to it, then the carbocation stays around, and so that affects the stability of it. The other one is electronics. Do the substituents around the cation withdraw electrons or donate electrons? We will talk about the electronics next week, because I thought it was going to be way too much to talk about both sterics and electronics in one session. So basically, if you if you go back to slide 4 and we look at the ions, those R groups, R1, R2, and R3, can either, through the single bond that we have, they can either donate electrons, meaning that increase the electronic cloud around the carbon, or they can withdraw electrons, meaning decrease the electronic cloud around the carbon. And the factors that affect that are electronegativity of those R groups as compared to that of carbon, and also whether there are resonance structures that allow me to draw a neutral carbon atom. And we see that we're going to see all of that next week. So let's go back to the sterics, and on the last slide, slide 8, I'm kind of showing you how the environment around the carbon atom, as we go from primary to tertiary, changes. These on the right-hand side is what we call the space-filling model. On the left-hand side is what we call the molecular model. So the molecular model for ethanol is CH3CH2OH. We can see on the left-hand side, the black balls are carbons, white balls are hydrogens, and the red ball is oxygen. So on the left-hand side, we see kind of how all of these atoms are connected to each other. And on the right-hand side, we see the space-filling model for ethanol. And so that basically, if we take all of that 50% probability space for electrons around the atoms and all that, you end up with something that looks like that. Again, this is a model and may not be the reality. But in any event, if you look at the right-hand carbon, the one to which the OH is attached, you see it's basically pretty open. It is just as open as the CH3 that's on the left-hand side. Well, maybe slightly, the other carbon maybe slightly crowding it more than the hydrogen would, but still it is pretty open. Then we go to a secondary carbon, to isopropanol. Now the backside of the carbon that the oxygen is attached to. So if I want to come in and attack that carbon and kick the oxygen out, I have to come in from the backside. The backside of isopropanol, the right molecule, is at 10 o'clock. And so if you look at 10 o'clock, you will see that now I have two carbon atoms with those two hydrogens that are crowding the central carbon. So my access to the central carbon between the secondary carbon and the primary molecule, the access has become a lot less. And if I go to the next one, which is tert-butanol, tertiary butanol, it has four carbons, one in the middle, three around it, and the OH is also attached to the central carbon. Now, if you look at the space filling model, we can't even see the central carbon, right? The other three methyl groups have almost completely obscured that central carbon. So if a nucleophile wants to go in there and attack the central carbon, it can't. It doesn't have any room to get there. The other methyl groups with their hydrogens and carbons repel that nucleophile can't get there. But we don't have that for ethanol. This was a description of steric hindrance, how going from a primary carbon to a tertiary carbon, sterics become more crowded, and steric hindrance become a much greater factor in deciding how the reaction goes. So I'm going to stop here, and hopefully you guys can come up and talk about this, because I really want people to understand this before I go into. Here I talked about the sterics around the central carbon of ethanol, or an alcohol, but not a cation. So how would the sterics affect the stability of a carbocation? We're going to talk about that next week, along with electronics and how choosing the right solvent in this reaction can help you modifying the electronics of the reaction to make one of these carbocations be more favorable than the other ones. So that concludes my talk for today, and please come up and let's have a chat going. Benjamin, you have any questions? Anybody in the audience has any questions?
Cat ions. I just have to say, whenever I hear cat ions, it's impossible for me not to think of cats.
Yeah, because when you say cations fast, it sounds like you say cat eyes. No questions?
Man, I don't have any questions. This is all uncontroversial science. I only do controversial science, Sam.
Well, I'm doing basic chemistry. How controversial can basic chemistry be?
I mean, that's the problem is you got to make it controversial. Then I can come in and make it interesting.
Uh huh. Yeah, so what we're talking about is really the first semester of organic chemistry. I was going back to my college OChem textbook to kind of figure out how they're presenting it. So I kind of used that. And I was like, yeah, it's basically the first 200 pages of the book. And that's where we are. Okay. If there are no questions, no comments, I mean, it doesn't have to be about this. We can just chat about science in general, anything. All right. So I'm going to play us out. Thank you all for joining us today. And don't forget, Tuesday, I'll be doing the continuation of the IP law room, finishing up trade secrets. And then on Thursday, I'll be continuing this conversation about the stability of carbocations. I've also put together a presentation on the pharma industry. Basically, not about medical science, but about pharma science. That basically, okay, you've identified the disease. Now, how do you know which compound is going to treat that disease? And how do you go about testing that? First chemically, then biochemically, then in cell cultures, then in animals, and then in humans. And what are the things that the FDA looks for to approve a drug, and what is phase 4, things like that. So I hope I'm trying to find a good time to present that. It's probably going to be on a Monday, but keep your eyes out in the scientific discourse room for that room. There's a lot of misinformation about the pharma industry on Clubhouse and outside, where people conflate they conflate the business of the drug industry and the science of the drug industry, and those two are completely different. They have absolutely nothing to do with each other, and so we're going to be basically focusing on the science of the pharma industry. All right. Well, I'm gonna play you the song "They Never Pay Me" by Gina Cecilia. I'm sorry, and it's about disparity in about the pay gap between women and men. I hope you guys have a great day, and if I don't see you, have a wonderful weekend, and talk to you guys in the future rooms. And don't forget, tomorrow John has his Bite of Physics room, so hope to see you there too. Have a good day, everyone. The room will end when the song ends. Thanks.
I try, but they always evade me. Why, oh why, oh why? Give me just a little bit. Give me just a little